Welcome to the comprehensive course on fundamentals and basics of blockchain technology, designed to guide complete beginners through the intricate world of blockchain. This course aims to demystify the complex concepts and technologies underpinning blockchain, providing a solid foundation for understanding its potential and applications across various industries. Blockchain technology, at its core, is a decentralized ledger that records transactions across a network of computers, ensuring transparency, security, and integrity without the need for a central authority. Originating from the digital currency Bitcoin, blockchain has evolved far beyond its cryptocurrency roots, offering solutions for secure and efficient transaction processing, data management, and much more. Starting with an introduction to what blockchain is, its history, and key terminology, this course delves into the mechanisms that enable blockchain's unique properties: decentralization, immutability, and transparency. You'll learn about different types of blockchain networks, including public, private, and consortium blockchains, and understand their respective advantages and use cases. As we progress, we'll explore the revolutionary concepts of smart contracts and decentralized applications, which extend blockchain's utility beyond simple transactions, enabling automated, programmable agreements and applications that run exactly as programmed without downtime, fraud, or interference. The course also covers the critical role of cryptography in blockchain, ensuring secure and trustless transactions, and dives into the consensus mechanisms that allow blockchain networks to agree on the validity of transactions. Practical applications of blockchain across industries such as finance, supply chain, healthcare, and real estate are examined, showcasing how this technology is being used to solve real-world problems. Additionally, we'll address the challenges facing blockchain adoption, including regulatory, privacy, and security considerations, and discuss future trends and the ongoing evolution of blockchain technology. By the end of this course, you'll have a comprehensive understanding of blockchain fundamentals, equipped with the knowledge to explore further applications, innovations, and opportunities in the blockchain space. Introduction to blockchain technology. This section introduces the foundational concepts of blockchain technology. It's designed to provide learners with a thorough understanding of what blockchain is, its history, key terminology, how it works, and the different types of blockchain. What is blockchain? At its core, blockchain is a distributed database or ledger that is shared among the nodes of a computer network. It stores information electronically in digital format. Blockchain is best known for its crucial role in cryptocurrency systems, like Bitcoin, for maintaining a secure and decentralized record of transactions. The innovation with blockchain is that it guarantees the fidelity and security of a record of data and generates trust without the need for a trusted third party. Key characteristics: decentralization. Unlike traditional ledgers or databases that are controlled by a central authority, a blockchain is decentralized and distributed across all participants in the network. Transparency. Every participant in the network can view the transactions stored in the blocks. Immutability. Once a transaction is recorded in a blockchain, it is extremely difficult to alter. History and evolution of blockchain. Origins. The concept of blockchain was first outlined in 1991 by Stuart Haber and W. Scott Stornetta as a method for timestamping digital documents to prevent backdating or tampering. However, it wasn't until 2008 that blockchain gained popularity with the release of the Bitcoin white paper by an individual or group under the pseudonym Satoshi Nakamoto. Evolution. From its initial application as the backbone of Bitcoin, blockchain technology has evolved to support a wide range of applications across various industries beyond cryptocurrency, including finance, healthcare, supply chain, and more. Key concepts and terminology. Block, a data structure used for keeping a set of transactions, which is distributed to all nodes in the network. Chain, a sequence of blocks in a specific order. Node, a computer connected to the blockchain network, which has a copy of the ledger. Transaction, the smallest building block of a blockchain system. How blockchain works, a simplified overview. Transaction creation, a user initiates a transaction, which is then broadcasted to the network. Block creation, transactions are collected into blocks by miners or validators. Block validation, network participants validate transactions within a block according to consensus rules. Chain addition, once validated, the block is added to the existing blockchain, making the transaction history unalterable and publicly recorded. Types of blockchain. Public blockchain, open to anyone, where anyone can participate in the process of block verification. Private blockchain, controlled by a single organization or entity, restricting who can participate in the network. Consortium blockchain, operated by a group of organizations, with pre-selected nodes responsible for the consensus process. Examples. Bitcoin, the first and most well-known application of blockchain technology, designed as a decentralized digital currency without a central bank or single administrator. Ethereum, a decentralized platform that enables smart contracts and decentralized applications to be built and operated without any downtime, fraud, control, or interference. Supply chain management. Companies like IBM have implemented blockchain to create transparent and secure supply chain management systems. This allows all parties in the supply chain to access the same information, potentially reducing disputes, delays, and errors. This section lays the groundwork for understanding the intricate details of blockchain technology, preparing learners for more advanced topics in subsequent sections of the course. Understanding decentralization. In this section, we delve into the concept of decentralization, a fundamental principle underpinning blockchain technology. Decentralization is pivotal in differentiating blockchain from traditional centralized systems and understanding its benefits and challenges. Centralized versus decentralized versus distributed systems. Centralized systems. These systems rely on a single point of control. For instance, most traditional banks operate on a centralized system, where all transactions and data are controlled and processed by the bank itself. This central authority has complete control over all operations and data, making it a single point of failure. Decentralized systems. In contrast, decentralized systems distribute control across multiple points. No single entity has complete control, reducing the risk of a single point of failure. Cryptocurrencies like Bitcoin exemplify decentralized systems, where transactions are verified by a network of nodes rather than a central authority. Distributed systems. These systems spread data across multiple nodes to ensure redundancy and reliability. While all decentralized systems are inherently distributed, not all distributed systems are decentralized. A distributed system becomes decentralized when control and decision-making are also distributed. The role of decentralization in blockchain. Decentralization is the core feature that makes blockchain revolutionary. It ensures that no single entity can control or tamper with the data, enhancing security and trust in the system. Decentralization is achieved through the use of consensus mechanisms, which require agreement among multiple parties to validate transactions and add new blocks to the chain. Benefits of decentralization. Enhanced security. By distributing data across a network rather than storing it in a central database, blockchain minimizes the risks associated with data breaches and cyber attacks. Increased transparency and trust. Every transaction on a blockchain is visible to all participants, ensuring transparency. This visibility helps build trust among participants, as every action is verifiable. Reduce censorship. With no central authority to control the network, it's incredibly difficult for any entity to censor transactions or data on a blockchain. Challenges of decentralization. Scalability. Decentralized networks can face scalability issues due to the consensus process, which can be slower and more resource-intensive than centralized systems. Energy consumption. Certain consensus mechanisms, like proof of work, require substantial computational power, leading to high energy consumption. Complexity and usability. The decentralized nature of blockchain can make it more complex for users to understand and interact with, potentially limiting its mainstream adoption. Examples: Bitcoin, the first decentralized digital currency. Bitcoin operates on a global network of computers that jointly manage the ledger and transaction processing, removing the need for a central authority. Decentralized finance. Platforms like Uniswap and MakerDAO operate on the Ethereum blockchain, offering financial services such as lending, borrowing, and trading without the need for traditional financial intermediaries. Decentralized autonomous organizations. These are organizations represented by rules encoded as a computer program that is transparent, controlled by the organization members, and not influenced by a central government. DAOs operate on blockchain technology and are an excellent example of decentralization in practice. In summary, decentralization is a key element that provides blockchain technology with its unique characteristics of security, transparency, and resistance to censorship. Understanding this concept is crucial for grasping the full potential of blockchain and its applications across various sectors. Cryptography and blockchain. Cryptography is the cornerstone of blockchain technology, ensuring secure and trustless transactions within a decentralized network. This section explores the cryptographic principles that underpin blockchain, ensuring data integrity, confidentiality, and authentication. Basics of cryptography. Cryptography is the practice and study of techniques for secure communication in the presence of third parties called adversaries. It involves creating and analyzing protocols that prevent third parties or the public from reading private messages. Key concepts: encryption, the process of converting information or data into a code, especially to prevent unauthorized access. Hashing, transforming a string of characters into a usually shorter fixed-length value or key that represents the original string. Hashing is a one-way function, meaning it cannot be reversed. Hash functions and their importance. Hash functions in blockchain. Blockchain technology uses hash functions extensively. Each block contains the hash of the previous block, creating a chain of blocks. This linkage ensures that any alteration of transactional data within a block would invalidate the hash and, by extension, the integrity of the entire blockchain. Properties. Deterministic, the same input will always produce the same output. Fast computation, the hash function should be capable of returning the hash of input quickly. Pre-image resistance, it should be infeasible to reverse the hash function to find the original input. Collision resistance, it should be infeasible to find two different inputs that produce the same output. Example: Bitcoin uses the SHA-256 hash function for mining and creating addresses. Public key cryptography and digital signatures. Public key cryptography. This is a cryptographic system that uses pairs of keys, public keys and private keys. The generation of such keys depends on cryptographic algorithms based on mathematical problems to produce one-way functions. Digital signatures. In blockchain, digital signatures are used to verify the ownership of a blockchain address. A user signs the transaction with their private key, and the network verifies the signature using the user's public key. This process ensures that transactions are secure and cannot be tampered with. Example: when Alice sends Bitcoin to Bob, she signs the transaction with her private key. The network nodes use Alice's public key to verify that the transaction was indeed signed by her private key and approve the transaction. Ensuring integrity and security in blockchain. Immutable ledger, the cryptographic linkage of blocks ensures that once a transaction is entered into the ledger, it cannot be altered, making the blockchain immutable. Secure transactions. Cryptography ensures that transactions are secure and tamper-proof. Users can transact directly without needing trust or a central authority. Examples: Bitcoin, the implementation of SHA-256 for hashing and ECDSA for digital signatures ensures the integrity and security of transactions on the Bitcoin network. Ethereum uses SHA-256 for hashing and also relies on public key cryptography to secure transactions and smart contract executions. In practice, smart contract security cryptography is essential for ensuring the security of smart contracts, which automatically execute transactions based on predefined conditions. For instance, a smart contract for an escrow service encrypts and secures the agreement terms, releasing funds only when those terms are met. Data privacy in blockchain applications that require data privacy, such as in healthcare, cryptography can encrypt patient records, ensuring that only authorized individuals can access them. Cryptography not only secures blockchain technology but also instills the foundational principles of integrity, authentication, and confidentiality. Understanding these cryptographic mechanisms is crucial for anyone looking to delve into blockchain development or deployment. Blockchain network and technology. This section delves into the technical structure of blockchain networks, explaining how they function, the role of consensus in maintaining integrity and trust, and the architecture that supports blockchain's unique characteristics. Anatomy of a block. Structure. A block in a blockchain is a container data structure that aggregates transactions for inclusion in the public ledger, the blockchain. Typically, a block contains a header, which holds metadata, and a body that contains transaction data. Header includes the previous block's hash, a timestamp, the nonce, and the Merkle tree root hash, which summarizes all the transactions in the block. Body lists all the transactions validated and included in the block. Example: in Bitcoin, a block structure facilitates the process of mining and transaction verification, ensuring the security and continuity of the blockchain. How transactions are recorded on blockchain. Transaction initiation. A user signs a transaction with their private key and broadcasts it to the network. Verification. Nodes verify the transaction's validity, including signature authenticity and the sufficiency of funds. Transaction pool. Valid transactions await in a pool until they are picked up by a miner to be included in a new block. Block creation. Miners assemble transactions into a new block and compete to solve a cryptographic puzzle. Consensus. Once a miner solves the puzzle, the new block is broadcast to the network. Other nodes validate the block and add it to their version of the ledger if it's accepted. Understanding blockchain consensus mechanisms. Consensus mechanisms are core to blockchain technology, enabling trustless and decentralized transaction verification and block addition. Proof of work. Miners compete to solve a complex mathematical problem. The first to solve it gets to add the block to the blockchain. This mechanism secures the network but is energy intensive. Bitcoin and Ethereum are prime examples. Proof of stake. Validators are chosen to create a new block based on the amount of cryptocurrency they are willing to stake or lock up as collateral. It's more energy efficient compared to POW. Ethereum 2.0 aims to use POS. Delegated proof of stake, a variation of POS, where token holders vote on a select number of delegates to validate transactions and create blocks. EOS uses DPoS. Popular consensus algorithms, proof of work, proof of stake, and others. Proof of work ensures security through computational work, deterring attacks by making them economically unfeasible. Proof of stake aims to reduce energy consumption and increase transaction throughput by selecting validators based on their stake. Others. Practical Byzantine fault tolerance addresses the Byzantine generals problem, allowing a distributed network to reach consensus even if some nodes fail or act maliciously. Hyperledger Fabric employs a variant of PBFT. Examples: Bitcoin and proof of work. Bitcoin's blockchain uses POW to secure its network, where miners solve cryptographic puzzles to validate transactions and create new blocks. Ethereum in transition to proof of stake. Ethereum is moving from POW to POS in its Ethereum 2.0 upgrade, aiming to become more energy efficient and scalable. In practice, supply chain management. Blockchain can provide a transparent and immutable ledger for the supply chain, ensuring the authenticity and traceability of products. For example, Walmart uses blockchain for tracking produce from farm to shelf. Healthcare. Patient records can be securely stored and shared on a blockchain, improving data accuracy and accessibility. Estonia's health system is an example of blockchain in healthcare. Blockchain technology's network and architectural principles provide the foundation for its decentralized, secure, and transparent characteristics. Understanding these aspects is crucial for leveraging blockchain in various applications, from cryptocurrencies to broader industry use cases. Smart contracts and dApps. This section explores the transformative concepts of smart contracts and decentralized applications, which extend blockchain from a simple distributed ledger to a platform for automated, trustless transactions and applications. What are smart contracts? Smart contracts are self-executing contracts with the terms of the agreement between buyer and seller being directly written into lines of code. They run on a blockchain, making the contracts immutable and the transactions they facilitate transparent and traceable. Key features: autonomy. Smart contracts eliminate the need for intermediaries, executing automatically based on predefined conditions. Trust. Encoded in a decentralized blockchain, smart contracts offer a high level of security and trust. Backup. Like the blockchain, smart contracts are duplicated many times over the network, providing exceptional resilience and redundancy. Safety. Encrypted and immutable, they provide a secure environment for transactions. How smart contracts work. Programming. A developer writes the conditions and outcomes of the contract in a programming language supported by the blockchain platform. Deployment. The smart contract is deployed to the blockchain, where it gets its own address. Execution. When predetermined conditions are met, the contract automatically executes the encoded instructions without any need for human intervention. Introduction to decentralized applications. dApps are applications that run on a decentralized network, avoiding any single point of failure. They use smart contracts for back-end code, running on a blockchain, and provide a user interface through which users can interact with the smart contracts. Characteristics. Open source code is typically transparent and available to all. Decentralized data and records of operation are distributed across the blockchain network. Incentivized utilizes cryptographic tokens to reward network participants. Protocol adheres to a standard cryptographic algorithm, often governed by consensus mechanisms. Use cases and examples of smart contracts and dApps. Finance. DeFi platforms like Uniswap allow for cryptocurrency exchanges without central intermediaries, relying on liquidity pools and algorithms to determine prices. Gaming. CryptoKitties, one of the first dApps to reach widespread popularity, enables users to purchase, collect, breed, and sell virtual cats on the Ethereum blockchain. Real estate. Platforms like Propi automate real estate transactions with smart contracts, enabling property buying, selling, and transferring process to be executed digitally and securely. Blockchain platforms and development. Ethereum, the first blockchain to support smart contracts and dApps, offering a robust ecosystem for developers. EOS offers a more scalable infrastructure for dApps, with faster transaction times and different governance models. Tron focuses on high throughput and supports a large number of transactions per second, aimed at entertainment and content sharing dApps. Examples in detail. Uniswap a protocol on Ethereum for swapping ERC-20 tokens without requiring buyers and sellers to create demand. Uniswap uses an automated liquidity protocol. Decentralized, a virtual reality platform powered by the Ethereum blockchain. Users can create, experience, and monetize content and applications, owning land as NFTs. Challenges and considerations. While smart contracts and dApps offer revolutionary potential, they also face challenges such as scalability, user experience, and security vulnerabilities. Ensuring code accuracy and security is paramount, as smart contracts are immutable once deployed. Smart contracts and dApps represent a significant shift towards automating and decentralizing digital transactions and applications. Their development and adoption are rapidly evolving, shaping a future where decentralized, trustless transactions play a critical role in various industries. Blockchain platforms and development. This section provides a comprehensive overview of blockchain platforms, focusing on their features, capabilities, and how they enable the development of smart contracts and decentralized applications. It also offers guidance on getting started with blockchain development, including tools and resources. Overview of major blockchain platforms. Blockchain platforms provide the infrastructure for developing and deploying smart contracts and dApps. Each platform has its unique features, consensus mechanisms, and development languages. Ethereum, launched in 2015, Ethereum is the first blockchain platform to support smart contracts and dApps. It uses the Ethereum virtual machine to execute code and relies on proof of work, transitioning to proof of stake with Ethereum 2.0. Ethereum's primary language for smart contracts is Solidity. Hyperledger Fabric, hosted by the Linux Foundation. Hyperledger Fabric is a modular blockchain framework that provides a foundation for developing applications or solutions with a modular architecture. It is designed for enterprise solutions, emphasizing privacy, scalability, and security. Smart contracts in Fabric are known as chain codes and can be written in Go, Java, or Node.js. Solana, known for its high throughput and fast transaction speeds, Solana uses a unique consensus mechanism called proof of history, combined with POS. It's designed to support scalable dApps and cryptocurrencies, utilizing Rust and C as its primary programming languages. Basics of blockchain development. Blockchain development involves several key activities, from smart contract development to front-end application construction for interacting with the blockchain. Smart contracts, writing business logic that runs on the blockchain, governing transactions and interactions. dApps development, building decentralized applications that interact with smart contracts, often involving web development skills to create user interfaces. Setting up a blockchain environment. Choose a blockchain platform. Select a platform based on the application's requirements, such as throughput, security, and language preference. Install development tools. For Ethereum, tools like Truffle Suite and MetaMask are essential. Development environment. Integrated development environments like Remix provide a convenient platform for writing, testing, and deploying smart contracts. Writing and deploying your first smart contract. Example with Ethereum. Write a smart contract using Solidity. Create a simple contract, such as a Hello World or a basic ERC-20 token. Test the contract. Use the Truffle Suite or Remix to test the contract's functions, ensuring it behaves as expected. Deploy. Deploy the contract to a test network using Truffle or through Remix directly. After successful testing, it can be deployed to the Ethereum mainnet. Example projects and use cases. Supply chain tracking. Utilize blockchain to create a transparent and immutable ledger for supply chain operations, enabling real-time tracking of products from manufacture to delivery. Voting systems. Develop a decentralized voting application that ensures security, transparency, and immutability of votes. Learning resources. Official documentation. Always start with the official documentation of the chosen blockchain platform for the most accurate and reliable information. Online courses and tutorials. Platforms like Coursera, Udemy, and YouTube offer comprehensive courses on blockchain development. Community and forums. Engage with community forums like Ethereum Stack Exchange, Reddit, and Discord servers dedicated to blockchain development for support and advice. Challenges in blockchain development. Blockchain development is an evolving field facing challenges such as scalability, interoperability between different blockchains, and user-friendly design. Developers must stay updated with the latest technologies and best practices to address these challenges effectively. Blockchain platforms and the development process offer a robust infrastructure for creating decentralized applications and services. By understanding the unique features and capabilities of each platform, developers can leverage blockchain technology to build innovative solutions across various industries. Cryptocurrency and tokens. This section delves into the world of cryptocurrencies and tokens, explaining their significance, types, and how they operate within the blockchain ecosystem. It also covers the concepts of initial coin offerings, security token offerings, and token sales, providing a comprehensive understanding of digital assets. Introduction to cryptocurrencies. A cryptocurrency is a digital or virtual currency secured by cryptography, making it nearly impossible to counterfeit or double spend. It operates on a blockchain as a decentralized ledger, maintained through a consensus mechanism like proof of work or proof of stake. Bitcoin, the first and most well-known cryptocurrency, introduced in 2009 by an individual or group using the pseudonym Satoshi Nakamoto. Bitcoin remains the most recognized and widely used cryptocurrency, serving as a digital gold standard in the industry. Altcoins refers to cryptocurrencies other than Bitcoin. Examples include Ethereum, Ripple, Litecoin, and many others. Altcoins often present themselves as improved or modified versions of Bitcoin, with some serving specific purposes or utilizing different consensus mechanisms. Tokens versus coins. Coins, typically, a coin has its own blockchain where transactions occur. Examples include Bitcoin on the Bitcoin blockchain and Ether on the Ethereum blockchain. Tokens are created on existing blockchains. Ethereum is the most common platform for token creation, supporting tokens through its ERC-20 and ERC-721 standards. Tokens can represent assets or utility. For example, DAI is a stablecoin pegged to the USD, and BAT is used in the Brave browser to reward users for viewing ads. ICOs, STOs, and token sales. Initial coin offerings. An ICO is a type of funding using cryptocurrencies. It's often a form of crowdfunding, although a private ICO which does not seek public investment is also possible. In an ICO, a quantity of cryptocurrency is sold in the form of tokens to speculators or investors, in exchange for legal tender or other cryptocurrencies like Bitcoin or Ethereum. Security token offerings. An STO is a public offering similar to an ICO but with regulatory oversight, where security tokens are sold. Security tokens are digital assets that derive their value from an external, tradable asset and are subject to federal laws that govern securities, offering investors some protection. Token sales. This term can refer to the sale of either utility or security tokens before they are listed on exchanges. The purpose is to raise funds for the project's development. Examples: Ethereum's ICO in 2014, one of the most successful ICOs, raising over $18 million and paving the way for the development of the Ethereum platform. The DAO, an example of a complex smart contract on the Ethereum platform that raised a record $150 million in an ICO, but was later hacked due to vulnerabilities in its code. BAT ICO, the basic attention token, raised $35 million in under 30 seconds. showcasing the massive demand and potential for ICOs to fund blockchain projects. Challenges and considerations. Regulation and compliance. The regulatory environment for ICOs, STOs, and token sales is evolving. Projects must navigate complex legal frameworks across different jurisdictions. Market volatility. Cryptocurrencies and tokens are known for their extreme volatility, which can lead to high rewards but also significant risks. Due diligence. Investors should perform thorough due diligence before participating in any ICO, STO, or token sale, considering the project's technology, team, and business model. Cryptocurrencies and tokens are integral components of the blockchain ecosystem, providing mechanisms for transactions, funding, and digital asset representation. As the blockchain space evolves, understanding the nuances of these digital assets becomes crucial for developers, investors, and users alike. Blockchain and industry. Blockchain technology's impact extends far beyond cryptocurrencies, offering transformative possibilities across various sectors. This section explores how blockchain is being implemented in different industries, highlighting specific use cases, benefits, challenges, and future prospects. Blockchain and financial services. Decentralized finance. DeFi uses blockchain to recreate traditional financial services like lending, borrowing, and earning interest in a decentralized, open access environment, bypassing traditional banks and financial institutions. For example, platforms like MakerDAO allow users to lend and borrow cryptocurrency, while Compound enables earning interest on crypto holdings. Cross-border payments. Blockchain facilitates faster and cheaper cross-border payments compared to traditional banking systems. Ripple is a notable example, offering real-time international money transfers with lower transaction fees. Supply chain and logistics. Traceability and transparency. Blockchain provides an immutable ledger, making it ideal for tracking the provenance and journey of products throughout the supply chain. IBM's Food Trust Network uses blockchain to enhance visibility and accountability in food supply chains, allowing participants to trace the origin and safety of food products. Counterfeit prevention. By ensuring the authenticity of products, blockchain helps combat counterfeits, especially in industries like pharmaceuticals and luxury goods. For instance, De Beers Tracker platform tracks diamonds from mine to retail, ensuring they are ethically sourced and genuine. Healthcare. Patient data management. Blockchain can secure and streamline the sharing of medical records, maintaining patient privacy and data integrity. Estonia has implemented a blockchain-based system to secure health records, allowing patients, doctors, and authorized parties to access real-time data securely. Drug traceability. Blockchain assists in tracking pharmaceuticals to prevent counterfeiting and ensure compliance with regulations. MediLedger is a project aimed at creating an industry-wide, blockchain-based compliance framework for the pharmaceutical supply chain. Real estate. Property transactions. Blockchain can simplify and secure the process of buying and selling property by digitizing records, verifying ownership, and automating transactions through smart contracts. Propi is a platform that enables online real estate transactions, making the buying process simpler and more transparent. Challenges and considerations for blockchain adoption. Scalability. High transaction volumes can overwhelm blockchain networks, leading to slow processing times and higher costs. Regulatory compliance. The decentralized and immutable nature of blockchain poses challenges for regulatory compliance, particularly in sectors like finance and healthcare, where privacy laws and financial regulations are stringent. Interoperability. Different blockchain platforms and protocols may not be compatible with one another, making data sharing and transactions across blockchains challenging. Future prospects. Integration with IoT. Blockchain could secure the vast amount of data generated by IoT devices, ensuring integrity and enabling automated transactions between devices. Sustainability and environmental monitoring. blockchain could play a role in tracking carbon credits and verifying sustainable practices, contributing to environmental conservation efforts. Decentralized identity. Blockchain offers solutions for secure, decentralized management of digital identities, giving users control over their personal data. Blockchain technology holds the potential to revolutionize industries by enhancing transparency, security, and efficiency. However, widespread adoption requires overcoming technical, regulatory, and operational challenges. As the technology matures and these issues are addressed, blockchain is likely to become an integral part of our digital landscape, reshaping how we conduct transactions and manage data across various sectors. Regulation, privacy, and security in blockchain. The increasing adoption of blockchain technology across various sectors brings to the forefront the critical issues of regulation, privacy, and security. This section examines these aspects in detail, providing insights into how they impact blockchain implementations and what measures are being taken to address them. Regulatory landscape for blockchain and cryptocurrency. Varied regulatory approaches. Countries around the world have adopted differing stances on blockchain and cryptocurrencies, ranging from supportive frameworks aiming to foster innovation to stringent regulations or outright bans. Key regulatory concerns. Anti-money laundering. Regulations require platforms trading cryptocurrencies to perform due diligence on their customers to prevent money laundering. Securities regulation. Many ICOs have faced scrutiny under securities laws, with regulators determining whether tokens constitute securities and thus fall under relevant regulatory frameworks. Taxation. The IRS in the United States, for instance, treats cryptocurrencies as property for tax purposes, requiring reporting of gains and losses. Example: the European Union's fifth anti-money laundering directive includes provisions aimed at increasing transparency in financial transactions, including those involving cryptocurrencies. Privacy concerns and solutions in blockchain. Privacy issues. While blockchain's transparency is one of its strengths, it also raises privacy concerns, especially in applications requiring confidentiality such as finance and healthcare. Privacy-enhancing technologies. Zero-knowledge proofs allow one party to prove to another that a statement is true without revealing any information beyond the validity of the statement itself. Cash, a privacy-focused cryptocurrency, utilizes ZKPs to enable encrypted transactions. Private transactions on public ledgers. Solutions like Ethereum's zk-SNARK integration and Monero's use of ring signatures ensure transaction details remain private, even on a public blockchain. Security issues and mitigation strategies. Security vulnerabilities. 51% attacks occur when a single entity gains control of more than half of a blockchain network's computing power, enabling them to double-spend coins and prevent new transactions from confirming. Smart contract vulnerabilities. Flaws in smart contract code can lead to significant losses. The DAO hack on the Ethereum network is a notorious example, where a vulnerability was exploited to drain millions of dollars worth of Ether. Mitigation strategies. Regular audits and security reviews. Conducting thorough audits of blockchain infrastructure and smart contract code to identify and rectify vulnerabilities before they can be exploited. Enhanced consensus mechanisms. Developing more robust consensus algorithms that are resistant to attacks. For example, Ethereum's transition to proof-of-stake aims to mitigate the risks associated with POW, including 51% attacks. Decentralization, enhancing the network's decentralization to prevent any single point of failure or control, thereby increasing security. Future directions. Regulatory clarity. As blockchain technology continues to evolve, clearer regulatory frameworks are expected to emerge, balancing the need for innovation with the protection of consumers and the integrity of financial systems. Advancements in privacy technologies. Ongoing research and development in privacy-preserving technologies will likely result in more sophisticated solutions that enhance privacy without compromising blockchain's inherent transparency and security. Security enhancements. With the increasing sophistication of cyber threats, the blockchain community is likely to continue focusing on strengthening security measures, including the development of more secure consensus protocols and the widespread adoption of best practices in smart contract development. The regulatory, privacy, and security aspects of blockchain form a complex landscape that requires continuous attention from developers, users, regulators, and other stakeholders. As the technology matures, addressing these challenges will be crucial for ensuring its sustainable and responsible growth across industries. The future of blockchain. Blockchain technology stands at the cusp of transforming a wide array of sectors, from finance to healthcare, supply chain, and beyond. This section explores emerging trends, technological advancements, and the potential future impact of blockchain technology. Emerging trends and technologies in blockchain. Interoperability. The ability of different blockchain networks to communicate and share information seamlessly is becoming increasingly important. Projects like Polkadot and Cosmos aim to create blockchain of blockchains, enabling interoperability and data exchange between disparate networks, enhancing efficiency and scalability. Decentralized finance, DeFi, continues to grow, extending blockchain from simple value transfer to more complex financial operations like lending, borrowing, and decentralized exchanges. DeFi aims to recreate and improve upon the traditional financial system by removing intermediaries and increasing accessibility. Non-fungible tokens, NFTs, have exploded in popularity, enabling the tokenization of digital assets, proving ownership and provenance. While initially popular in art and gaming, NFTs are expanding into new domains, including intellectual property, real estate, and identity verification. Blockchain and the intersection with AI, IoT, and big data. AI and blockchain. The integration of artificial intelligence and blockchain can enhance the security and efficiency of AI algorithms, while blockchain can benefit from AI in terms of improved scalability, security, and consensus mechanisms. For example, AI can optimize energy consumption in mining processes or enhance smart contract efficiency. IoT and blockchain. The Internet of Things generates vast amounts of data that need secure, efficient management. Blockchain can provide a secure, immutable ledger for IoT data, ensuring integrity and enabling trustless transactions between devices. This can significantly impact smart cities, supply chains, and energy management. Big data and blockchain. Blockchain can contribute to the field of big data by providing a secure and transparent environment for data collection, storage, and analysis. It can ensure the integrity and verifiability of data sources, which is crucial for accurate big data analytics. Ethical considerations and social impact. Digital identity. Blockchain offers solutions for secure, self-sovereign digital identities, giving individuals control over their personal information. This has significant implications for privacy, security, and the fight against identity theft and fraud. Supply chain ethics. By providing transparent tracking of products from origin to consumer, blockchain can help enforce ethical labor practices and sustainability standards, ensuring products are ethically sourced and produced. Financial inclusion. Blockchain and cryptocurrencies can provide financial services to the unbanked and underbanked populations worldwide, offering access to banking, loans, and financial instruments without the need for traditional banking infrastructure. Predictions and possibilities for blockchain technology. Widespread adoption. As technological and regulatory hurdles are overcome, blockchain is expected to see broader adoption across industries, streamlining processes, enhancing transparency, and improving security and efficiency. Evolution of national and digital currencies. With the advent of central bank digital currencies, blockchain is set to redefine the very nature of money and how it is used in society, potentially leading to a decrease in the use of traditional fiat currencies. Transformation of industries. Industries like healthcare, education, and entertainment are beginning to explore blockchain's potential, hinting at a future where blockchain could underpin significant aspects of society. From voting systems and property rights to personal data management and beyond. The future of blockchain is not without its challenges, including scalability, energy consumption, and regulatory hurdles. However, its potential benefits in creating a more transparent, efficient, and equitable global society are immense. As we look ahead, the ongoing evolution of blockchain technology promises to bring about significant transformations across multiple facets of our lives and industries. Getting started with blockchain development. Embarking on blockchain development is an exciting journey that opens up a world of possibilities for creating decentralized applications, smart contracts, and more. This section provides a roadmap for beginners to start their blockchain development journey, covering tools, resources, and communities that can help. Tools and resources for blockchain developers. Solidity for Ethereum developers. Solidity is the primary language for developing smart contracts on the Ethereum blockchain. Beginners can start with the Solidity documentation and use Remix, an online IDE, for writing, deploying, and testing smart contracts. Truffle Suite, an essential tool set for Ethereum developers. Truffle Suite includes a development environment, testing framework, and asset pipeline for blockchains using the Ethereum virtual machine. It's great for deploying smart contracts and building dApps. Ganache, part of the Truffle Suite, Ganache is a personal blockchain for Ethereum development you can use to deploy contracts, develop applications, and run tests. MetaMask, a browser extension that acts as a bridge between browsers and the Ethereum blockchain, allowing users to manage accounts and interact with dApps seamlessly. Hardhat, another popular Ethereum development environment designed for advanced developers, offering features like network management for deploying to any Ethereum network, automatic smart contract testing, and console logging. Building your first blockchain project. Understand blockchain fundamentals. Before diving into coding, ensure you have a solid understanding of blockchain basics, such as how blockchain works, what smart contracts are, and the principles of decentralized applications. Learn a smart contract language. If you're interested in Ethereum, start with Solidity. There are plenty of tutorials and online courses available to get you started. Experiment with development tools. Install tools like Truffle Suite, Hardhat, or Remix to start experimenting with smart contract development. Develop and test your first smart contract. Begin with something simple, like a Hello World smart contract, to understand the development and deployment process. Participate in hackathons and projects. Engage with the community by participating in hackathons, contributing to open source projects, or collaborating on forums. This experience is invaluable for learning and networking. Community and continuing education. Online forums and communities. Platforms like Ethereum Stack Exchange, Reddit's r/Ethereum, and the Ethereum Developers Discord server are great places to ask questions, share knowledge, and connect with other developers. Conferences and workshops. Attend blockchain conferences, workshops, and meetups to stay updated on the latest trends, technologies, and best practices in blockchain development. Continuous learning. The blockchain space evolves rapidly. Follow blogs, YouTube channels, and online courses to keep your knowledge up to date. Platforms like Coursera, Udemy, and crypto-specific learning platforms offer specialized courses in blockchain technology and development. Example projects to inspire. Token creation. Start by creating your own ERC20 token on Ethereum, which can represent anything from a currency to voting rights or points in a loyalty program. Decentralized voting system. Build a D-app that allows secure, transparent voting, demonstrating how blockchain can mitigate issues associated with traditional voting systems. Supply chain tracker. Develop a D-app that tracks the journey of products from manufacture to sale, showcasing blockchain's ability to enhance transparency and trust in supply chains. Getting started with blockchain development requires a blend of theoretical knowledge and practical experience. By leveraging the tools and resources available and engaging with the blockchain community, aspiring developers can pave their way to building innovative, decentralized applications that could transform industries. Conclusion and next steps. In this final section, we wrap up our comprehensive course on the fundamentals and basics of blockchain technology. We've traversed the landscape of blockchain, from its inception and underlying principles to its multifaceted applications across various industries. This journey has equipped learners with a solid understanding of blockchain technology, its potential, and its limitations. Now, let's summarize key learning points and explore how to stay updated with blockchain developments and the opportunities that lie ahead in this dynamic field. Recap of key learning points. Blockchain fundamentals. We started by understanding what blockchain is, its decentralized nature, and how it differs from traditional databases. Key concepts like cryptography, consensus mechanisms, and the anatomy of a block were discussed to lay the groundwork for more complex topics. Smart contracts and dApps. The course highlighted the revolutionary role of smart contracts in automating and securing transactions on the blockchain, along with the development and significance of decentralized applications that operate on these principles. Blockchain in various industries. We delved into real-world applications of blockchain across sectors such as finance, supply chain, healthcare, and more, showcasing the technology's versatility and potential to streamline operations, enhance transparency, and ensure data integrity. Regulatory and ethical considerations. The discussion on regulation, privacy, and security underscored the importance of navigating the evolving legal and ethical landscape surrounding blockchain technology. Future prospects and emerging trends. Finally, we explored future directions for blockchain, including interoperability, advancements in consensus mechanisms, and the integration of blockchain with other cutting-edge technologies like AI and IoT. How to stay updated with blockchain developments. The blockchain field is rapidly evolving, with new technologies, platforms, and applications emerging regularly. Staying informed about these developments is crucial for anyone looking to build a career or foster innovation within this space. Here are some strategies to stay current. Follow industry news and blogs. Websites like CoinDesk, Cointelegraph, and The Block provide timely updates on blockchain technology and cryptocurrency markets. Engage with community forums. Platforms such as Ethereum Stack Exchange, Crypto Twitter, and various Discord and Telegram groups are excellent resources for real-time discussions and insights from the blockchain community. Attend conferences and webinars. Blockchain conferences, webinars, and meetups are great opportunities to learn from experts, network with professionals, and discover the latest trends and projects. Continuous learning. Enroll in advanced courses, participate in hackathons, and contribute to open-source projects to deepen your understanding and gain practical experience. Opportunities in blockchain technology. The demand for blockchain expertise is growing across sectors, presenting a wealth of opportunities for developers, consultants, project managers, and entrepreneurs. Emerging areas such as DeFi, NFTs, and blockchain-based identity solutions are just the tip of the iceberg. Professionals who can navigate the technical, business, and regulatory aspects of blockchain are well positioned to lead innovation in these spaces. Final thoughts? As we conclude this course, remember that the journey into blockchain is one of continuous exploration and learning. The technology's potential to reshape industries and redefine paradigms is immense, but realizing this potential requires dedication, creativity, and a willingness to embrace change. Whether you're a developer, business leader, or enthusiast, the blockchain space offers a frontier of opportunities to those ready to explore and innovate. Embrace the challenge, continue learning, and become part of the blockchain revolution that is set to transform the digital and physical worlds in profound ways.